Okay, so this is how to solve a problem for the tension in the string when the object's going in motion in a uniform vertical circle. That is, it doesn't speed up and it doesn't slow down. So it might not be possible to actually do this with an object on a string. So we always talk about, maybe it's on a rod or something like that makes it go at a constant speed. Because this thing is naturally going to speed up and slow down as it goes around a circle. Okay. But for now, let's just keep the velocity constant, that whatever the speed is at the top, that it's the same at the bottom somehow, right? We have to be clever about it, right? So you'll read in the book, they'll say it's cleverly twirled so that the velocity is constant, right? And in this problem, we've got a 5 kilogram object. Let me draw this guy here. That's a good circle. It's a good circle. Okay, so here is our 5 kilogram object, right? It's a 3.75 meter radius circle, and we need to know the force, and it's going 9 meters per second. Somehow it's going at a constant 9.00. It's very accurately measured, right? Meters per second. And we want to know what the tension is in this thing at the top, and we want to know what the tension is at the bottom. So here's the same object. Now it's at the bottom. Presumably at the bottom it's still going, it's 9 meters per second. Okay. And then this is still 5 kilograms. There we have it, right? Okay. Now, the good news is that all we have to do is we have to just use what we know about masses on strings and F equals ma. Yes? Now, the bad news is the same thing, right? Because maybe we didn't learn that in the previous chapter, right? So what's the trick if I've got a mass on a string? What is the trick? There's a trick. It's not really a trick, but if we got that part of the test wrong, it's kind of a trick. Yeah? There are two forces acting on this, yes? One of them is the tension in the string. The other one is gravity. Can we forget gravity in this case? No. Okay. In fact, I know when I was twirling that thing around and around, at the bottom there was a lot more force I had to exert. At the top there was less. I could feel it. More, less. More, less. Okay. All the time, over and over, right? So the good news is that we're going to solve it the same way we've always solved mass on a string problems, only the acceleration is going to be this acceleration. Now here's the only tricky part, is that at the top, which way is the acceleration? It's always toward the center, but at the top, which way is it? Up or down? The acceleration is toward the center, and so it's down. Okay, so the acceleration is negative, right? At the bottom, which way are we accelerating? We're actually accelerating toward the center. We're always accelerating toward the center, but in this case, it's up. So our acceleration here is positive. So whatever we figure out the acceleration to be, at the top, it's a negative acceleration. At the bottom, it's positive. Now, does it matter on these F equals ma problems if you get the acceleration wrong? Yeah, it matters, doesn't it? Yeah, you get the problem wrong. Okay? I felt sad marking a lot of test questions wrong. On that first page, it was like actually a negative acceleration. People got positive. It's like everything was right except for that minus sign, right? So we have to be very careful about that. But having said that, let's have at it, right? So what do we have to calculate? What's the first thing we should do, probably? Find the acceleration. Yeah, it's not a bad place to start. So the acceleration of this thing is going to be v squared over r, so it's 9 squared divided by 3.75 meters. What is that? Okay. 9 squared divided by 3.75. 21.6. So this is going to be a case of, isn't it going to be a case of that I have to actually pull it down at the top? Yeah? Isn't that right? I'm going to have to pull down on that thing to make it accelerate downward that fast, because you can only accelerate downward for free in Earth's gravity 9.81, correct? Okay, so I'm going to have to actually pull this thing down. If you get an acceleration, by the way, that's less than 9.81, what it means is that it's not going to work with a string. It would have to be like a stick, right? And we'd have to actually push up on the object to keep it from falling off the circle, right? But this is our acceleration. We'll just go with that. What's another thing that we probably have to calculate before we start setting stuff up? Weight! The weight. Yeah. And that's funny because I just coughed, and didn't that cough sound a lot like weight? That's weird. Not at all. Okay, good, because I know you guys would have thought of that on your own. Okay, so the weight of 5 kilograms is 49.05. So 5 times 9.81. Okay, this force is, I believe it's 49.05. But my obsessive compulsive disorder will not allow me to just remember that. Okay, so there's newtons there, right? And so now we've got at the top we have gravity, which is acting downward, right? 49.05. And we have tension, and we know darn well that the tension is going to be a downward force. Don't we know that? Right? But the tension, I'm going to say the tension is like, we don't know, right? I'm just going to say it's like a push me, pull you thing, right? But it'll end up being negative, shouldn't it? Shouldn't the force of the string be downward? I believe it will be because this is bigger than 21.6, right? How about at the bottom? What forces do we have? Well, the same thing, 49.05 down, right? Okay, that one's shorter, so I gotta make this one shorter, right? So 49.05, and then of course here we're gonna pretend and be all coy that we don't know the tension is upward, but it has to be up. It's always up at the bottom, right? So here we've got the tension equals, we don't know, right? Okay. And now all we have to do is set up Newton's second law twice, okay? At the top, our forces are unknown force, T, right? Okay, minus gravity, T minus 49.05. Those are the only forces, right? Okay, and then it's 5 times, what's our acceleration? 21.6, but it's toward the center. The center is below us, and so the acceleration is negative 21.06. That, by the way, is the only thing, 21.6, not 0.6. There we go. Right? So at the top, we're accelerating. At the top, the center is down. Right? And now we can solve this thing. T should be a negative number. It's kind of weird to solve it. I should really just call it F. Right? So let's go 5 times negative 21.6 plus 49.05. And we get that the tension is negative 58.95 newtons. Yeah? So again, the two forces are an unknown force. Gravity is down, m times a. And the only tricky thing is that since the center is below us, we have to make the acceleration negative. Yes? Good news is it's not a new thing. We've done this before. Bad news is it's really confusing, isn't it, sort of to remember that this is a negative acceleration? Is it? Kind of is, yeah, a little bit, okay? At the bottom, the only thing that's different, okay, is that we still have the same two forces. We have a different tension. I'll call it T prime or something like that, right? Minus 49.05. Okay, so some unknown tension minus 49.05 equals 5 times. And then what's the difference? Which way are we accelerating at the bottom? We're accelerating toward the center. The center is above us, so we're accelerating up, right? So this is positive 21.6. Yeah? So 5 times 21.6 plus 49.05. And it's 157. T is yay. Okay. So that is method number 1 for solving it. Wouldn't it be cool if there was a pirate way? Yeah. Okay, if you do the pirate way, if you choose to do it the pirate way, okay, you have to say Argalot, Archimedes, in a barrel of rum. Okay, or something like that, on a dead man's chest. Or I don't know, there it is, right? Okay, the pirate way goes, we just go with the G force. Okay, for the pirate way, at the top, right, what do we feel? We feel the ride minus 9.81, don't we? That, by the way, is what's going